I am here today at LFAB Space in the L Space building downtown Tunis with my fellow friend and guest Mohamed Haroun joining us from Philadelphia, USA. So I want to talk a little bit about L Space and LFAB Space more, and then Mohammed will talk about NYC Makerspace, and then we'll kick it off to the 3D printing part. So first of all, L-Space is Tunisia's first social innovation hub, and it gathers software activities, entrepreneurship activities, environmental activities, as well as making and Fab Lab related activities. So for those of you who do not know what a Fab Lab is, so it's basically a fabrication laboratory, and the concept started maybe like 10 or 20 years ago in the US and then expanded all over the world. So these fabrication laboratories are places where people can share and exchange and use common resources such as 3D printers, laser cutters, and electronics, and all sorts of machinery. Some fab labs are small, some fab labs are big, and there are also mobile fab labs, basically fab labs on wheels that can go anywhere and do actually workshops and allow the people to experiment and exchange knowledge everywhere. So in Tunis, L-Space has been leading two Fab Labs, so from creation to implementation and management. So LFAB Space and LFAB Space LAC. So LFAB Space, where I'm at right now, is centrally located in downtown Tunis and offers a wide array of services and workshops and activities and programs for youth in Tunisia to empower them to start their own companies and to make whatever they want to do. Of course, except the illegal stuff. And then our second Fab Lab, in collaboration with Mohamed Haroun, is in LAC, Les Berges du Lac, which is the business district of Tunis. And it's basically complementary to the Fab Lab we have downtown, as it is catered to startups and very state-of-the-art technology. And of course, in both Fab Labs, we have 3D printers, laser cutters, CNC machines, as well as workspace and resources and tools that people can use. So yeah, during this coronavirus pandemic, Fab Labs around the world have been very, very active in basically saving people's lives. And most commonly, you've seen those face shields that are made everywhere. And in Tunisia, we started by being part in the 3D printing network, where people actually joined in with their 3D printers to print an open source design and then deliver them to the nearest hospitals. And in that way, we protect the frontliners against the coronavirus. So now I'll leave the floor to my friend Mohammed to tell us a little more about NYC Makerspace, what it is and how are things going.
Sure. So, hi, my name is Mohamed Haroun. I'm former manager of the Columbia Makerspace. And in my time before that, I was the manager of the mechanical engineering teaching laboratory, where I taught design and fabrication on the different machines that we had. So we had mills, lathes, like heavy metal cutting equipment, and we also had 3D printers and laser cutters and new digital fabrication equipment as well. So after that, I was promoted to being the manager of the Columbia Makerspace, and I stayed there for a while. And throughout that time, I saw that makerspaces, especially in the US, but I believe all around the world, they're really they were often for people who had the means to access them. So the average cost of a makerspace or of makerspace membership in New York City or even across the US is between $80 and $150. And when you're on the lower end of that, that usually just gives you access to the space itself and not to the machinery that is in that space. That you can come when you come in, you're on, but then you have to pay for the usership of the machinery. And that was really like prohibitive to the majority of people, because $100 a month, and then you have other added costs. It usually ends up becoming $300 a month, and the majority of people that live in New York City can't afford that. Hello? Can you guys hear me?
Yeah, we hear you. Continue. Don't hesitate.
Oh, okay, sorry about that. Adnen just messaged me saying the internet shut down. So what ended up happening was I started to search in my area, and I was living in Harlem for a while. And I don't know, I'm sure everybody knows what Harlem is. It's a kind of poorer part of New York City, or less developed part of New York City, for spaces where I can make a makerspace. So at that time, there was a space in there. I was also working with the Parks Department in their art program. And they wanted a 3D printer. So we had a 3D printer donated to the art program in the local Parks Department Recreation Center. And during my talks with them, I asked them whether they would be interested in making a makerspace. And I knew that I could probably reach out to libraries, and this is something that's happening across the US, where libraries are starting to host makerspaces. But what I really wanted to do was be located in a space that was focused on recreation rather than learning and education. This way, I'm kind of engaging people without any kind of pressure related to learning or prestige that comes with learning something new. And from my experience, learning something because you're enjoying it creates better outcomes. I've learned this at Columbia, where students actually do better in the university when they're part of the race car team or the rocketry team, because they're learning the engineering concepts because they want to finish this project. They have a project that they're very interested in, that they want to make succeed. So that was the story of the beginning of NYC Makerspace. We created a partnership, and we started our first makerspace in Harlem in a place called Marcus Garvey Park. And there we put 3D printers, laser cutters, and we started to host courses. And the goal of NYC Makerspace is that it's for free as long as you have a park membership, which is around, it's around $100 a year rather than $100 a month. And you get free access to the space. You have to pay for the materials that you use, and we do have some materials that are kind of for experimentation that's there. But that brings down the cost of interacting with this advanced manufacturing equipment, or this kind of digital fabrication equipment, and new tech industry to be a lot cheaper and a lot more affordable for the average person and the working class individual.
Great. Thank you, Mohammed. This has been very insightful and very beautiful to learn, and potentially some good news will be shared across the coming days, basically between about LSpace and NYC Makerspace. So I want to just take a brief moment here to say like about the achievements of 3D printing here in Tunisia, and of course across the world. So basically, the thing started when the coronavirus situation started in China and then made its way throughout the world. So we have a partner Fab Lab Mindanao in Philippines, and they've already been struggling with the different challenges of the coronavirus situation, which made them innovate and use 3D printing in different ways, as well as laser cutters, but especially 3D printing. And then from there, we exchanged with them, and we learned a lot about what is happening and everything. And then we kind of adapted to our own situation in Tunisia. And of course, the beauty of open source technology and open source design is that people can build and can change and can get inspired and make new things for the greater good. And especially here, one of the things that we focused on is protecting the doctors and nurses who are the frontline defense against this virus, or against the spread of this virus. Um, so the 3D printing part comes in very handy, and honestly, I'm a business major. I'm not a technician or an engineer, but I've seen the. I only realized the impact of just a very like small scale 3D printer only now, when the world is going on running like in all sorts of ways, to basically get back to 3D printing and as a tool for innovation in this time of crisis. So later on, once I think Mohammed is offline for a bit. So once he's joining, he will be basically introducing what is 3D printing, what is a 3D printer, and what are the different parts, and how basically to function one on the spot. So you'll have open source design online on websites like Thingiverse or GrabCAD, and of course you can just email ahla@lspace.org, or on our Facebook page, and you'll find a lot of information and resources, and we can send you the designs to print at home, or if you have access to a 3D printer. Um, so hi, welcome back, Mohammed. You want to start?
Sorry, the internet all over the world is it's slow because everyone's at home. I got kicked off. I apologize.
No worries. So yeah, I was introducing you and your basically workshop. So feel free to go ahead.
Awesome. So I don't know how many of you have heard about 3D printing. 3D printing is actually relatively old. It's not a new technology. It's actually was the first instances of 3D printing happened in the 70s and 80s. It really didn't become ubiquitous, or didn't become prevalent all over the world, and as as widespread as it is now, because there were advances in both software and hardware side of the equation. I don't know if you guys can still hear me. On the hardware and software side of the equation, start until around 2005, 2006, and these included the beginning of microcontrollers, the beginning of so things like precursors to Arduino, but the beginning with Arduinos and Raspberry Pis, and the decreased cost, and the widespread learning of code that became a lot cheaper to do, because obviously the internet allowed that to happen. As that started to happen, 3D printers became a lot more accessible, a lot cheaper for the general public. So what is 3D printing? A really simple understanding of 3D printing is melting, or there are several different types of 3D printing, but the prevalent one, and the one that is most available and the cheapest that's in the world, is something called FDM, or Fusion Deposition Modeling. Okay, so Fusion Deposition Modeling is a fancy way of saying melting and depositing, and creating a model of what you're melting and depositing, right? So what that means is, if you guys can see, this is a nozzle, right? And it means that you're literally you're taking the plastic, and usually the plastic that's being used is PLA, polylactic acid, or ABS, and I can't remember what ABS stands for. And it's melting the plastic and then extruding it out of a nozzle. And the way that happens is it literally starts layer by layer at the lowest level, and moves and deposits one layer, and then moves up, deposits a second layer, and so on and so forth, until it builds a full model upwards. This method is called FDM. And there are other methods as well. There's something called SLA, stereolithography, and the way that is that kind of 3D printing happens is there is a pool of photocurable resin, which is like glue that hardens when you shine light on it, high intensity light on. And there is a platform that dips inside of this pool of photocurable, this pool of goo, right? And when it dips inside of that pool of goo, underneath there is the pool is kind of in a glass or like a plastic clear container, and underneath there is a laser. And so the first layer, the platform dips inside. The layer shoots up, the laser shoots up light, and then hardens the photocurable resin to the first layer, moves up, and it shoots up another set of lights, and it hardens the next layer, and so on and so forth. So as you can see, what's happening here is layering, right? So, it basically, you create the process is it takes a 3D model, creates layers out of that 3D model, and it informs the printer how to deposit that layer over over time and over a certain area. So let's go further into the parts of a printer. And after we cover what the different parts of the printer are, we're going to go into the actual process of putting an object into the 3D printer, right? So I have here with me, I just actually found this printer in my garage, and I assembled it this morning. This is a printer called AnyCubic. There are many 3D printer companies out there, and the most, I guess, widely used printers in the world are that are consumer printers are Prusas, and they're called Prusa MK2 or MK3. I think they're up to MK3 right now, and Ultimaker, and those are the most widely used printers that exist out there. And then there used to be the most widely used, or the first commercially available consumer product printer that existed in the world, was something called MakerBot. And MakerBot actually was replaced as number one by Ultimaker. And I'll go over the reasons why MakerBot was supplanted by Ultimaker soon. So let's talk about the different parts of the printer. So I showed you earlier the nozzle over here, and this is called the so this is the heating element. As you can see, this area. Let me see. So this area is the heating element, and that's where the plastic starts to melt. And then at the bottom, this is the this area right here is the nozzle. And this nozzle comes in different diameters. Okay, so like right now, I believe this is a 0.4. Yeah, it's a 0.4 diameter, and that's 0.4 millimeters, right? On here, I believe is also another 0.4 millimeter diameter. And so this area, all it's responsible for is heating the plastic and depositing it. Now, there's another part of the head that's called the extruder. And the extruder is basically a motor that pushes the filament, which is the plastic that's used. And this is a roll of filament. And it's just basically a plastic that has been molded into a thin thread, right? And that filament goes and it is pushed through this tube. And this is called a Bowden's tube. Right, and it's pushed through this tube, and then when it's pushed all the way through and in through the head, okay, and that's basically what's happening. Now, in order to push it through, we need a motor to drive this filament, and that motor exists back here. So, turn this printer around. So when we're loading the filament, we load it into here, and it comes out and it grips, that motor grips it. And I don't know if you guys can see this, but there's a little gripper that the motor is held onto. It pushes the filament through and into the Bowden. So So again, this is the motor right here. And the gripper is right there. You see that wheel, and it's pushing the plastic through into the Bowden tube, and that comes out over here. You know, the Bowden tube continues in the front, and the nozzle is right underneath. Okay, so that's how the head mechanisms works. And so this extruder that's in the back that I just showed you, this extruder can be there's two different types. There's back-driven printers, and there is front-driven printers. So the back-driven printers are the ones that have extruders behind them. They're in the back of the machine, and they are depending on the tension that is in the Bowden tube to push the material through and into the heating element and the nozzle, right? So it literally is pushing the material through, and if this Bowden tube didn't exist, it would just push material out and everywhere, and it wouldn't, you have to have this Bowden tube as a guide in order to have the material enter the nozzle. Now, there are also front-driven systems, like the Perusa model that I talked to you about is a front-driven system, meaning that motor that's in the back is actually right above the nozzle. So it's literally right here, right above the heating element. And it drives the material into the nozzle right away. So while one pushes, the back-driven system pushes the material through the Bowden tube and into the nozzle, the front-driven system pulls the material off of the roll and pushes it directly into the nozzle. The Bowden tube isn't really there for any purpose rather than just as a guide and not to get the material everywhere. So that's the different types of nozzles and heads. I don't know if anybody has questions. Please feel free to add questions, and I'll answer. So the other part of the printer is the base, right, or the build platform, and that build platform is right here. So I have this. Sorry, it's a new printer, so I still have it removed here. So this is the build platform. There's usually some kind of glass or metal plate, all right? And that is often heat, so you can set the heat based on the different material that can set the heat that's appropriate. And the goal of the build platform is just to be a place where the material or the model sticks to the surface of the machine. And so that's basically the concept behind printing. When you load a file, it begins the printer. It's a G-code file extension that you're loading, and that G-code gets sliced into layers, and those layers are deposited one at a time into the machine as it builds upwards. The next part is going to be about the how to actually create that file and what are these files that we are going to print. So let me look.
Hello. Oh, I think Mohammed's internet got cut off. Wow, it's a problem everywhere about this infrastructure, internet, and hospitals and everything. Wow. Okay, Okay, he's rebooting. Cool. So, guys, if you're following us, feel free to check online the software called Pura, and you can basically install it. It's open source, it's free. Just download it, and Mohammed will get you going with it as soon as he's back. So it's Cura, Pura. We'll input the website on the chat box on the YouTube channel. Cool. And also, do not hesitate to ask questions along the way. Do not wait until the end. I mean, we will respond to questions at the end of this event, but feel free to post your questions on the chat box at any time. Cool. I'm just joining.
Adnen, check below on the footer. You have like the message.
Yep.
You can check, you have like questions.
Oh, sure. 1 second, I can't see it. The button or the direct extrusion? I think that's a question that goes to Mohamed. I think the direct extrusion is always. Yeah. Yes. All right, still waiting on Mohamed to join. So meanwhile, I can share a little bit of information about the 3D printers we have at Fab Space, at both Fab Space in Tunis and in LAC. So there's a G-Tech A30. It's one of the best in the entrée de gamme 3D printers. And then we have Raise N1. And then we have an Ultimaker 2.
I'm about to introduce something called the slicer software.
All right, cool. Welcome back, Mohamed.
There are many types of slicer software. And I think Walid actually asked me which one is better about extrusion. So direct extrude the direct extrude better than the in tube. Use both. The direct extruder, as I said, puts the motor right above the nozzle. And I don't know if you guys can see me. Yeah, sorry about that. So direct extruder puts the nozzle right. The extruder right above the nozzle. The motor's right above here, and it's pulling the material in and through the heater and the nozzle right away. This is better because there aren't usually with we have a lot of problems with the back-driven system, because Bowden tubes get scratched on the inside. Also, dust accumulates on the inside. Also, there is resistance inside of the element and the nozzle over time. As you use them more, there's buildup from melting that plastic. All right, and what ends up happening is that buildup creates more and more resistance in the nozzle and the extruder area, which causes you to extrude slower from there and puts more stress on the Bowden tube, which eventually pushes the Bowden tube out of its location, and then the print fails and there isn't enough extrusion. So it actually decreases the rate of extrusion in your when you're printing over time. So yeah, so there's definitely a clear winner between those two, and that is definitely the front-driven system, not the back-driven system with the Bowden 2. There's a lot less failure that happened with the front-driven system. So back into what is a slicer software, and what is the point behind the slicing? All right, what are we doing when we're slicing? So when you're about to 3D print, you basically need a 3D model, right? So that 3D model is, you could create that in in a kind of CAD software, so SolidWorks, AutoCAD. There's what else is there? CATIA, Pro Engineer. There's a million CAD softwares that exist out there, and then you export something called an STL file. And the STL file extension, it's a stereolithography. And what it is it basically creates your 3D model, which is based on parameters, right? It no longer cares about your CAD parameters. When I say parameters, as in, I mean, this is kind of an example that I'm going to use. I say, oh, well, there is a axis line that goes through this hole that defines this circle. Axis line that defines the bigger circle, and so on and so forth. All of those little details, it ignores all of those little details, and it just creates surfaces and edges, right? And that's what a stereolithography file says. It estimates the design, your CAD model design, using surfaces and edges. So it basically creates like, kind of not NURBS, but like triangular shapes, and it cuts your model into like little tiny triangles, and then it estimates the surfaces and edges of your model, and that's stereolithography, or a stereolithography file. So an STL file is created. After it's created, and you have to import it into your slicer. So that slicer is a sorry, I'm trying to actually launch the slicer here. I had to restart my computer to make sure that it is not it's not taking any extra bandwidth from any other program. So that slicer, what it does is it takes your model and it slices it into layers, right? So you have, and if you kind of, I'm going to try to come really close. If you look at this model, this is actually a very well done model. This is a very well done model, and you can see, like, if I get really close to the camera, you can see the little layers that are on this. That's because the layer height, and we'll discuss layer height in a minute. It is very thin, right? So it's a very small layer height, so you get a very fine thought. It's estimated the design of your file really well. Then so that's basically what the slicer is doing. So it's basically creating what we call G code, right? Which is general code, is machine code, so that your printer can read that G code and then out the plastic in the correct location. So what does that G code do? It basically tells the printer, move the head to this location, extrude this much material in this location at this rate, at this speed. And then move it to here and extrude at this speed, and so on and so forth. And it's building out that that material over, or say that layer, and it's telling the nozzle or the head where to go to build that layer, then how much to move up, and then where to go to build the next layer, and so on and so forth. And that's basically the idea behind the slicer software. As this old computer loads. Where is it? And I will show you the different parameters that we'll be setting in Cura. Okay. Okay. There we go. All right, let's hope that fixes it. And let's look at where Kira is. All right, I think I'm almost ready to share my screen. I'm sorry about this. Just taking forever to load for some reason. Sorry, guys, it's just a really long time to load Kira, and I don't want to. It's a mistake to restart my computer. Even my task manager isn't responding. Okay, I'm just going to use an online slicing software until Cura decides it's going to work. That's what I'm going to do. It's the best option.
just for our followers, if you have any question, don't hesitate to ask.
Yeah.
So
Yeah,
it's really important this time because it's like loading really, really slow. So don't hesitate to just ask him.
Sorry about that. So, okay, Cura versus Simplify 3D or Prusa Slicer or versus Idea Maker. So I have the most experience with Cura and Simplify 3D. So Simplify 3D is the least buggy and the most reliable of all of the softwares that are out there. Cura is actually the number 2. It's pretty close to it because Ultimaker has poured a lot of money into it. Prusa Slicer isn't that great and you don't have as much control, or it's not as clean in terms of showing you what the control is. The user experience for Prusa Slicer and Idea Maker isn't very friendly. In terms of the OS, I've only used Windows for any of these software. I mean, I've only used the Linux for development. So yeah, so any of this actually works. Any of those actually work. The most important thing is actually to know what the different aspects, or what are the different things that your or different parts of your printer that are working, right? So, or what are the different parameters that you're changing, and you can find those parameters. It might take time because the user experience isn't that great, but you'll find those parameters across all. They're the same parameters. All FDM printers or fusion, melting and pouring, fusion deposition modeling FDM printers are the same. The parameters that you're changing are the same. They are, and we're about to go through them. Layer height, infill, wall, wall line count, wall thickness, top and bottom thickness. Those are the main ones that you're changing. And your, whether or not you're, whether or not you're, what parameters you're changing are all that matter. Let me, I think I am almost there. This is very strange. Okay, here is finally starting. Are there other questions? It's just a few minutes to get. Okay, there we are. All right, so I think. All right, I'm ready to share my screen. All right. So I just found an online slicer software for us to use while Cura loads, and it's called Astoprint, which is, I'm finding out now, is not very good. Is not very intuitive service. Let's see. Yep. And shoot. So this is Astoprint. Let me go back to like the main screen. And it allows you to do all these things. So there's a design library, G-code viewer, so it'll show you where your G-code is moving and so on. And then it tells you, okay, well, these are the third-party apps that they have that you can upload files from. So you could either design your files, or usually there's many platforms now that have like a library of STL files that you could just grab from and alter. The most famous of them is Thingiverse. So Thingiverse.com. And My Mini Factory is another. There is Instructables. There's a whole list of, as you can see, these are some of the more famous ones that are out there that will have the files for you, and you can adjust them either on your own. There's something called Mesh Mixer. These are on your programs that you install on your computer. Then there's online software like the easiest one to use is Tinkercad, where you could just upload the STL file and then be able to tinker with it online. It's an Autodesk software. So down here is the printer itself and the printer management. So the first one that you're selecting is the printer profile, which is what type of printer are you using, right? So here I chose the MK2. So if I add a new printer profile, in every slicer software out there, you have to select what printer you're using, because in order for companies to be able to capture market, they usually create a slicer software that is accessible to. I don't know what just happened. They usually create a slicer software that is accessible to all different types of printers. So I don't know. I think I may have. Can you guys still hear me?
Yeah, we hear you. We have like some question too.
Yes.
Awesome. Okay, cool. What is the difference between STL binary export, STL, ASCII export? Okay, so the STL binary versus ASCII, these are just methods for, so ASCII is like basically the type of code that is, the keyboard that's being used. So these are different. There are two different types of exporting the file. Binary is more stable than ASCII in terms of getting the exact design that you need, but it's usually a larger file size. But in terms of what you get at the end of the day, there really isn't a noticeable difference that you see like using a naked eye, right? Like there's no real major difference except file size. And I believe Kira is about to launch. So that's basically the main difference between the two. So as I was saying, the first thing that you set up when you're loading your slicer software is what printer are you using. And as I said, usually the companies create a slicer software that is available with all different types of printers in order to kind of capture market and to show, hey, look, our slicer software is this clean, is this nice, is this easy to use? Why don't you use our printers as well? And that's kind of the way it's done. Cura, even though it was created by Ultimaker, you can use Cura for all different types of printers. Here in Astroprint, it gives you a list of the different printers that you can use. And I chose the first one, and I've already loaded it, the Prusa. Let's see if they have Ultimaker as well. Yep, they have Ultimaker. And then from there, that's the manufacturer, and they want to know the printer model. So I'll say the 2 plus extended, whichever, 2 extended. And you'll add that profile. And what that does is, based on that printer profile, your slicer software knows, okay, well, these are the different adjustments to G-code that I need to make in order for it to work on that specific printer, right? So G-code is code that's used for all different types of machines, not just for 3D printers. It's used for mills, lathes, anything on an axis that moves. And here, that's basically what's going on with these printers, is that you have 3 different axes, the X, Y, and Z, and you have the extruder as well. And those are being controlled by G-code. And the way that G-code looks is, like, for example, G001 is line motion, right? G003 is an arc motion. And then you just put like a coordinate after that. And besides, then there's other codes that are actually related to, and we call that M code, to the specific machine itself. And that, will kind of tells the G code what are the extents of the machine, what can be, what can be created from your STL file. that's basically the point of selecting the printer. It tells your slicer software, okay, you're outputting this G code, and these are the extents of the machine. This is the machine profile. The build plate is this large. The nozzle diameter is this large. The distance between the extruder and the nozzle is this much, and therefore it adjusts that G code that it's outputting to fit the printer. Now let's go back into the Kira has started. That's actually great. And that's, by the way, this is Kira, guys. And agree. Let's just add the S5. Sure. So as you can see, I'm choosing the printer type. I feel like explaining here is a lot more useful than Astroprint. And after that, it will improve. It'll put in the printer, and it'll show you the build plate that you're using. And then up here, you can change what material you're using. So here, as I said, the two main print materials for FDM printing is PLA and ABS. And then you could choose the material and who makes the material. That actually, all these minor things matter. So there is material that is better quality than others, and that really depends on the cost that you're willing to spend. Also the nozzle diameter, so they call it print core. So here, as I said, we have a 0.4. This goes to 0.8 for this specific printer. And you notice here there's AA and BB, and that's because the Ultimaker, the one that we chose here, the Ultimaker S5, is a tool nozzle printer. It has two nozzles that you can feed material to, and that gives you two abilities. The first ability is to say, oh, well, I'm going to use a model material like ABS and PLA in one nozzle, and something called a support material, and I believe it's PVA, the support material. And what that does is you can create objects like this, this gear all in one print. And the way that you do that is you lay down a model material, and then in between all of the gaps and underneath any kind of overhangs, you put a support material there, and you're able to melt it out in water or some kind of abrasive liquid afterwards. Then you are able to choose your printing profiles, right? So here, what they mean is this is the layer height, right? And you can actually go into custom, and this is actually great because the first one is quality. And remember how I showed you the different layers on the gear that I was showing you earlier? So the layer height is really determines the quality of your project, because the thinner the layer height, the more accurately it's displaying the surface of your model, right? The thicker the layer height, it's kind of like a pyramid, right? You've seen the step pyramid of Egypt. That's kind of approximating a layer, and then you have the three main pyramids in Giza, and that's you still have layers, but they're much thinner in layer height. So that's kind of what you're doing. You're approximating the surface using the layer height. So the thinner the layer, the cleaner the surface, the closer the approximation. Then you have something called shell, right? So the shell are things like wall thickness, the top and bottom thickness, and the wall, the line count. And let me kind of stop sharing here and show you that what I mean by that. So if you guys can see, I don't know why this is asking me to sign up, but if you guys can see here, there is a little wall. Please let me know if you cannot see for some reason.
Oh, it's fine. We can see.
Sign up. Okay, so there's little walls that it builds around the material, and before it lays what we call the infill inside of that inside of the material. So there we are. So yeah, so there's, let me see here, trying to get some light on it. But yeah, so it lays down the walls around, and then after it lays down the walls, it starts to lay the fill on the inside. And hopefully in our next session, I'll show you the material while it's being laid down. And I will share again my screen. Back to Kira. All right, awesome. So that's what wall thickness are, and that's what top and bottom layer height is. So it's in millimeters. You could say, okay, the wall line count. So how many times is it going to go around and create walls before it starts to put in the fill that's in the center? Then top and bottom thickness is the same thing. So how thick do you want the top and bottom, and how many layers do you want that in? How many times is it going to go around and put at the bottom, like how many layers is it going to put on the bottom before it starts to get into infill? And what is infill? So infill, which is the next thing that we set, is the material on the interior of your model, right? So it's done putting the outside extents of your model. It's done putting the wall. It's done putting the bottom layer, and now it's now filling the inside, and that's what infill is. And the different parameters that you're changing on that is the density. So how dense do you want it to be? Meaning like, okay, am I, obviously, and the pattern. So it creates the pattern. It could be a triangle. As you can see, there's many different types of patterns. I usually use grid, the grid pattern. So grid is just basically a hashtag, right? Pattern on the inside of the material. And how thick do you want that hashtag, right? Do you want me to fill the interior completely using a hashtag pattern, right? Or do you want me to only fill 20% of the interior and leave or whatever percent or some percentage of the interior? And that is all dependent on how much stress your part is going to be feeling or facing, right? So if you have a product or if you have a project where it's a doorknob or if it's an axle on a motor, for example, or something that's going to see some amount of stress, you obviously want that infill to be higher, right? So that your part is stronger. If you have a model like, I don't know, you're printing a Pokemon, for example, and it's just going to be a model that you put on your desk, then that doesn't need a higher, a greater infill. That just needs enough infill to keep that model from collapsing in on itself when you hold it, right? So you want like a lower infill density. So like a general guideline for a model that is something that is visual, like again, a statue, you want something between 15 and 25% infill, right? For something that is going to, see some kind of force upon it, then you go into above 50% infill to make sure that model doesn't break apart when it's seeing that force. The next thing that is usually changed is the material temperature. That's usually set once you select the what kind of material you're using. It has a library that it sets. Now this temperature actually varies, and it actually varies by color, and it varies by the manufacturer of that material. So darker colors actually you want to set to be a little higher. So and also the diameter of your material. Here we're using a thinner diameter material, and it's a 0.4 nozzle, and this material I believe is 0.125 thickness, and it goes up to 3 millimeter, 0.15 thickness, and it goes up to 3 millimeter thickness. For the 3 millimeter thickness, the 200 degrees here goes up to 215 to 230, and for the 0.15 millimeters, 0.175, sorry, 1.75, 1.75 millimeters, that stays around 200 degrees Celsius, and you can bring it up all the way to 207, 210. Again, it's based on color and it's based on the manufacturer. So the lighter colors you can set to be 200, 195. And all that, all the effects of that is just how well does it stick to itself when it's printing layer by layer. The build plate temperature is important because that sets, that affects the sticking of that material. Obviously, you want your material to stick to the build plate and to not be moving around, right? When it's printing, it has to stay there until it's done with the whole print. Again, that's dependent on the color of the material. It's also dependent on how old the material, how long the material has been sitting around, and the manufacturer. Speed, also, you want to, all these things have, when it comes to the infill, the layer height, those affect the speed of how fast your print is going to be. So the thinner the layer height and the more infill that you go, the longer your print is going to take. So, because it has to take more layers if you have a thinner layer height. And if you want a greater infill, if you want the part to be more tough, it has to put in more material on the inside. And since it has to put more material in on the inside, it takes longer to lay down that material. So print speed is varied with that, depending on the quality of your printer. So if you have a printer that is serviced regularly and it's relatively new, you can actually increase that print speed to be higher. Also, you can have a higher print speed if you have a front-driven system, right? If you have a good extruder, which has two of the little pulleys that I had showed you, and it's a front-driven system, the print speed can actually go up to 100 millimeters per second. Travel speed is if your system is well damped, meaning that there's no vibration that's going to end up affecting your print, then you can increase the travel speed as well. The last thing that there's two final things that I want to discuss before going into kind of closing this up, which is the support material and build plate adhesion. So support material is the material that it's laid down underneath any kind of model material. So when you have an overhang meaning imagine you have like a model, and there is a piece of it, let's say an arm, that is sticking out over empty space. So underneath that empty space, since you're making things layer by layer, you have to put down some support material in order to make sure that arm doesn't fall apart, doesn't fall down. And in here, when I select that I do want that support material laid down, it asks me, obviously from what extruder, because as we discussed, this type of printer has two extruders, and whether I want it just touching the build plate or if I want it everywhere. So that arm could be over the build plate, could be over this build area, right? Or that arm could be over another part of the model, right? So if I select touching build plate, it's only going to produce support material over the build plate, underneath, between the build plate and underneath that arm. If I say it's everywhere, then it's going to put support material anywhere there is an overhang, right? Something that is overhung, that like an arm. Even if it's between the model material and other model material, or between the build plate itself and the model material. So that's the idea behind support material. And as I said, there's two different types of support material. You could use, for example, if it's a single extruder, not a double extruder, then it just creates less dense material as support material. So it goes underneath that model area, and it lays down that support material. It's the same as the model material. It's PLA, but it's less dense. So it's easier for you to come in and break it out and clean up that surface. Then if you have a double extruder, you could use something called PVA, and then that PVA you use that extrudes from your second extruder, and when you're done, you just drop it in water and it melts away. And what's good about that is that it gives you a much cleaner surface because you're not there kind of cutting away at your model material, and then you have to sand and do a lot of post processing. What's bad about PVA is often it's very finicky. And your extruder fails off, like the PVA extruder, the support materials extruder fails often. Because what happens is when you're done printing, when your PVA hardens, it blackens and actually creates clogs in your nozzle. So I actually don't enjoy dual extruders. I don't think that they're efficient enough. I don't like the technology. And my experience using them, it failed it once every 3 times. There are different PVA types that are more expensive that actually don't fail as often. But I said you have to be willing to spend the money on it. Finally is build plate adhesion. So build plate adhesion is a material that is built around, that is made around the base of your model, right? So let me stop sharing again. And I will go, hopefully my camera will start. So it's built around the base of the model, and you can have, there are 3 different types. There is brim, as you saw inside of inside of Cura. There is a stage, and there is brim, stage, and let me find the last one, skirt. Okay, so the skirt is basically something that is, it's just basically a line of material that it creates around, not even touching your model, right? And that's when you start your print, it creates that skirt, and then goes and starts creating the base of your the bottom layer of your model, and goes on from there. Brim actually creates kind of like a hula hoop around your part itself. It creates like a border area of extra material around your part, and that is just there so that it can hold the material to the build plate, right? So that you don't have a situation where part of your print starts coming off of the build plate, and then your print's all kind of messed up. Finally, you have stage, and a stage, it builds a stage underneath your model. The importance of build, when is it useful to build a stage? It's useful to build a stage when you don't have a flat surface on the bottom of your model. If you don't have a flat surface, you can fix that by creating support material, obviously, but you still have a problem with build plate adhesion, right? Because the support material is supposed to be less dense than your model material, right? So you have less dense material that's holding your model to the plate. So a stage literally builds a stage underneath your model, which has a flat surface, and therefore it keeps the adhesion high. And then between the what you're printing and the build plate, and then from there it starts to build out the support material underneath to your model. Now that's useful for things like, and I feel like the most use that I've got from it was when I was printing molecules for a biolab in the university, and as you know, molecules don't have any kind of flat surface on it. So there, no matter what orientation I tried to put it onto the printer, it was never going to adhere. It was never going to stay in one place on the build plate. So there, it was very useful having that stage function. And that's basically all that you're adjusting in the ST and in your slicer software. So generally, just kind of as a recap, you have your model, you save it as an STL file in your modeling software, and then you upload it in your slicer software. And let me share my screen again. You upload it in your slicer software, and you adjust. There are 3 main parameters to adjust, and that is layer height, because again, you're only putting in the material once. You're only putting your printer once, because you're not going to be changing printers constantly. So you adjust your layer height. You adjust if you want, you can adjust the shelf thickness, right? How thick you want the walls and the top and bottom. You adjust your infill depending on whether this model that you're creating is going to be something that takes kind of pressure, or if it's just a model that you're putting on your desk to enjoy. It's a visual thing. And you're adjusting the support material, whether there is overhangs on your model, or if it's kind of like a box, or there's no overhang, and therefore you do not need support, right? And finally, you adjust your build plate adhesion, whether you want skirt, brim, or raft. Sorry, stage or raft. It's there are two different ways of saying it. So raft is what a stage is, and that's basically it. From there, you you prepare your model. It automatically generates your G code. You save it onto your it's usually an SD card. And then you import that SD card into the printer, press print, and you're ready to go. I hope that we can have a secondary time to meet up, and I'll have a printer running at that point, and we can go through the process and have a model there, and we'll be slicing the model during the course.
Thank you, Mohamed.
I appreciate you guys. Thank you guys so much for listening in. Please respond to Adnen if you'd like a secondary meeting time, and we can set that up within the next couple of days. And I'll have more. I'll have this printer running again. I literally just found it. I've been searching for this printer for the past couple of days in my garage, and we'll be able to set it up and have it running. I'm sorry for the internet interrupts. I think it's global. Everybody's online right now because nobody can go out.
Sure. Thank you so much, Mohamed. We really appreciate you joining in and sharing some of your experience with us. And so for everyone who is with us and for those who are joining later or just joined now, you can see the recording on YouTube, on the YouTube link. And please do not hesitate to ask any questions in the comment section, as well as to reach out to us as LSpace or FabSpace. And we'll surely have more events to come. Thank you all, and have a nice day.
Thanks, guys.